Alright, we're picking back up with equilibrium. Today we're going to talk about something called the reaction quotient, which is symbolized by the variable Q. We'll also discuss Le Chatelier's principle, which is just fun to say. So, Le Chatelier, if you want to practice pronouncing that. And then we'll talk about how you manipulate K and Q if you reverse a reaction, for example, or maybe you multiply the coefficients by 3, or perhaps you're going to put two reactions together. How would that change their K values or their Q values? So first off, we'll talk about what is Q and how do we calculate it and what does it tell us, and then move into Le Chatelier's principle. So those are our goals for today. The reaction quotient Q answers the question, how can we tell if a system is at equilibrium? So if you are posed with a question, so think Q, question, it asks you, are you at equilibrium? Or which way will you go to establish equilibrium? Will you proceed to the reactants or the products to reach equilibrium? Will there be more of this or that as you proceed toward equilibrium? Those sorts of questions about, are you at equilibrium? And if you're not there, which way are you going to get there? Those questions should prompt you to think about this reaction quotient, Q. So Q allows us to tell if something is at equilibrium. Here is an example problem in which we would employ Q, and we'll kind of get into what Q is and how we use it. In this example problem, they give us the K value, and they're at a certain temperature, and then we see our reaction. A chemist comes across this system, so let's say a chemist has a mixture of these three chemicals in some container, and you see the concentrations of each one there. This is a little different from what we saw previously, because if you remember in the last section, we always had like two reactants and no products yet. So we knew that the reactants were going to come together to make products. But in this case, you've already got some reactants and some products. So the question the chemist is asking is this system that I have, is it already at equilibrium? And if not, which way is it going to go to get to equilibrium? So those sorts of questions prompt us to use Q. Q is simply K when we're not sure if we're at equilibrium. Okay, Q is the same thing as K when we're not sure if we're at equilibrium. So it is products over reactants raised to their coefficient, exactly the same as K. The difference is we may or may not be at equilibrium. We have a question about if we're at equilibrium. So products over reactants raise their coefficient. In that particular reaction that we saw on the previous slide, there were no coefficients, so there's no exponents here. We just plug in the concentrations that they gave us. And we find that Q is 15.6. All right, if we look back, K was 0.042. 0.042. Let's write that down over here. 0.042 was K, and Q is 15.6. So Q is much greater than K. Now let's think about how both of them are calculated. On the top here we have products, and on the bottom we have reactants. So currently Q is too large, because remember K is the goal. K is equilibrium, and Q is telling us where we are right now. So our quotient is currently too large, which means we have too many products and too few reactants. So what's going to happen to reestablish, or establish for the first time maybe, equilibrium? We're going to have to get rid of some products and get more reactants. So how do we do that? If Q is too large, the reaction will proceed to the left where the reactants are, so that the reactants go up and the products go down until the system reaches equilibrium, or until that ratio is 0.042, as we see for K. So Q tells us whether or not we're at equilibrium, and if we're not, it tells us which direction we need to go, left or right, to reach that equilibrium. so toward the reactants or toward the products. Here is that shown visually. So there's our reaction. We said we had too many products, so we need to use those products and make some more reactants. So our reactants are going to increase while our products will decrease. And that's going to happen until Q is equal to K, until the system reaches equilibrium. So here's our guidelines. If Q is larger than K, we have too many products. So we're going to continue to increase the reactants until we reach equilibrium. So the reaction will go to the left. If Q is less than K, that means, if you think about the quotient, the products are on the top. We don't have enough products if Q is less than K. So the reaction is going to go to the right to increase the products until the equilibrium is established. If Q is equal to K, then that tells us that the system is at equilibrium. So it will continue to move toward reactants and products at the same rate, and none of the concentrations will change. It is already at equilibrium. Le Chatelier's principle works off this idea of Q. And Le Chatelier's principle says that if you have a system that's already at equilibrium, so your Q is equal to your K, and then you stress the system somehow. And so a stress is going to be something that makes Q go up or makes Q go down. That stress will then cause the equilibrium to shift in order to reduce the stress or to get back to K. There are only three things that can stress a system, and that would be a change in pressure, because if you think about Kp, if you change your pressure, that's going to change your Q value. If you change your concentration, that is going to change your Q value as well, and you'll have to switch back to get back to K. If you change the temperature actually changes the K value, so then the system will have to shift to balance back to the new K value. So let's put a star by that one. This is actually changing the K value. These two change the Q value, and then we'll shift to get back to K, but this one actually changes the K value, or the equilibrium constant, and so the system will have to shift to adjust to that. Alright, so how does this work? First off, what happens if we change the pressure? If we increase the pressure on a system, that's going to change our Q value. And as a result, the system is going to shift toward the side with fewer moles of gas to reestablish equilibrium. The change in pressure changes the equilibrium concentrations, but not the equilibrium constant. Okay, so from this slide, what do we need to know? If the pressure increases, we're going to shift toward the side with fewer moles of gas in order to reduce the stress. So think about it. If you have a system and you make the container smaller, so you put more pressure on that system, the system, that's a stress on the system. So what the system is going to do is going to shift so that there's fewer gases in the container, and that will reduce the shift. So it's going to go toward the side, whether that's reactants or products, where there's fewer moles of gas. And in doing so, it's going to reestablish that equilibrium. When it gets to a reestablished equilibrium, we may have new concentrations or new pressures, but the ratio does not change. So this change does not change our K value, as we said before. It only changes our Q value until we get to shift back to K. All right, here's an example of that. If you look at the top here, we have a reaction in which 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas. So over here we have 4 gas moles on our reactant side. And then on the product side, those come together to make 2 moles of ammonia gas. So 2 moles of gas over here. So if we take and increase the pressure on this system, okay, and to do that you just make the volume smaller. So when the volume goes down, the pressure goes up. If we increase the pressure on this system, it's going to shift to make more ammonia. And in doing so, it's going to make there be less gas molecules in the container. So if you look in this example over here, we've got 14 gas molecules, and these are at equilibrium, and then we stressed it out by pushing down, so it shifts, so now there's only 10 gas molecules. Right? The opposite is true if we decrease the pressure. So if the pressure on a system is decreased, then that's going to change your Q value. If you think about your pressure systems, you've got pressure products, pressure reactants. So if you decrease the pressure on the system, and you do that by increasing the volume, then the reaction is going to shift to the side with more moles of gas. So if pressure is decreased, we're going to go where there's more moles of gas. Again, this does not change your K value. It only shifts the reaction to reestablish that same K value. So if the pressure is decreased, you got more room for the particles to move around. So they will produce more gas particles. If you increase the pressure, like we saw previously, will produce less gas particles. So those are the inverse of each other. All right, we're going to see that right here where we have the same system again. So we have our nitrogen and our hydrogen. There's 4 moles of gas on the left, and our ammonia with 2 moles of gas on the right. We have our system with 10 gas molecules in it. We increase the volume, which decreases the pressure. So we have more room for those particles to move around. So we're going to shift this time toward the reactants because that's where the more gas particles are located. All right? So less pressure, more gas molecules, more pressure, less gas molecules. All right? Another stress is increasing concentration. If the concentration of one of the species in an equilibrium is increased, so let's say you add some reactants, well, now you're going to have too many of those. So when you do that, you're going to shift to reduce the concentration of that species. Okay, so if the concentration of something is increased, you will shift to reduce the concentration of that thing. When you do that, you're trying to reestablish Q to be equal to K. Because when you add something, you're either making your Q too big if you added a product, or your Q too little if you added a reactant, and you've got to shift to get back to K. This does not change the K value at all. All right, for example, here's our same system again. Here it is at equilibrium, just hanging out at equilibrium. And let's say we add more NH3. Remember that Q is products over reactants. So if you add some more NH3, that's going to make your products too big. So that's going to make Q bigger than K. Well, that's a problem. So how do we get back to K if Q is too big? We've got to shift to get rid of that excess. So we're going to be shifting back toward the reactants if we add a product. So here they added in 5 NH3. So we are not at equilibrium anymore. How do we get back there? How do we get back to equilibrium? We're going to take some of those NH3s and we're going to make some reactants. So we'll shift to the left. So they took one of those NH3s and they used it to make some more reactants as we're shifting back to the left. That means that NH3 is still higher than it was before, but it's not as high as when you first added the stuff. But your N2 and your H2 are going to be greater than they were before. So if you look over here at your final, you've got more stuff in there than you did before. However, the ratio at equilibrium should be the same. Okay, when you do products over reactants, raise their coefficient, we should get the same value when we get back to equilibrium. Even though we have more stuff in there, ratio, ratio, ratio is what it's about at equilibrium. All right, let's talk about the opposite. What if we decrease the concentration? So if the concentration of something is decreased, we'll shift to increase the concentration of that thing. So if something is decreased, we're going to move so we can increase its concentration to get back to K. Again, this does not change the K value. We're trying to get back to K because we messed up Q when we changed the concentrations. All right, here's an example. Here we are, we're hanging out at equilibrium. Notice there's a lot of molecules in here, but the ratios should be the same if we're at equilibrium. Okay, then we are going to remove some NH3 this time. All right, so let's think about our K value. If we remove some NH3, Q is products over reactants. So if we remove it, that makes Q go down. So Q is now less than K. So how are we going to get Q to get back to K? We got to move to make more products because we took them out. So now we don't have enough. So how do we make more products? Well, we have to use reactants, right, to make products. So we're going to use some of our reactants to make some more NH3 to get back to equilibrium. All right. Another stress that can occur related to concentration is if you add some solvent, like water, to the system. That solvent changes the concentration of everything. Right? It's going to make everybody's concentration go down. But one side will be affected more than the other, and that's the side with more particles. So, if you see this stress where you add solvent, that would be usually adding water, then Q changes, so we've got to get back to K. How are we going to do that? We're going to shift to the side with more particles to reduce the stress. It's just like the gas stresses when we increase the volume, is exactly like that. So if we increase the volume in an aqueous solution by adding more solvent, there's more room for those particles to move around, and so we're going to shift toward the side with more particles. Again, this change does not affect our K value. Here's an example of that. If you have hydrofluoric acid, which is a weak acid, it dissociates some and also comes back together, so we see a double arrow. If we have that in a small volume of water, and then we double that volume of water, basically, so we're adding more solvent, the reaction is going to shift to the side with more particles. In this case, we only have one particle as a reactant and two particles as products, so the reaction would shift to give us more of these products in that case. So you see in the first example on the left, you have 14 reactants. And then when you add more water, you now only have 8 reactants because more of them have broken apart into these particles that are our products. All right, lastly, the next or the last shift that we're going to cover, or stress, is if you change the temperature. And this is the only stress that will change the equilibrium constant. Okay, changing temperature is the only stress that will change the equilibrium constant. So in order to figure out how temperature affects a system, you have to know if heat is a reactant or a product. So you have to ask yourself, where's the heat? Where's the heat? Remember, if it's an exothermic reaction, then heat will be a product, like it is in this case. But if it's an endothermic reaction, then heat will be a reactant. So if we're dealing with changing temperatures, we got to know where's the heat. In this case, heat is a product. So if we cool down the reaction, we're taking away the heat. And remember, we said that if you remove something, you've got to make more of it. So if we cool down the system, we're taking away the heat, so we're going to shift to produce more heat. If heat is a product, as it is here, and we heat up the system, then we've got too much heat, so we're going to shift to relieve that stress or absorb the heat, decrease the amount of heat. So heat is treated just like any other reactant or product. If it goes down, we move toward it, and if it goes up, we move away from it. The only thing we have to figure out is where's the heat. So if it's exothermic, we're going to have heat as a product, but if it's an endothermic reaction, we'll have heat as a reactant. Now this does change our K value. So if we shift to the right, we're making more products, so that's going to make our K go up. But if we shift to the left, we're making more reactants, so that would cause our K to go down. And again, this is the only stress, temperature is the only stress that can change our K value. Alright, so this table does a good job of summarizing what we've seen today in terms of the stresses that could be applied to a system, what that would do to the system, and then why that would occur. So it starts with the concentration. If we increase the concentration of a substance, we're going to shift away from that increase because the extra concentration needs to be used up. If we decrease the concentration, we'll go toward that substance to produce more to make up for what was removed. Pressures. If we increase the pressure, we're going to go toward fewer moles of gas. If we decrease the pressure, we'll go to more moles of gas. If we increase the temperature, we'll go away from heat or energy. And if we decrease the temperature, we'll go towards the heat or the energy. Now there's a few changes that we need to make on this chart, and so I'll point those out here. These Y's don't really do a good job of describing the reasoning here, so we'll X those out. This should say endothermic. Okay, so we'll put that there. And then this one is indeed exothermic. So if we decrease the temperature, we're going to favor moving in the exothermic direction so that we can make up for the heat lost or produce more. However, if we increase the temperature, we're going to use up that extra heat. So we're going to favor an endothermic reaction. Now, a couple of notes that we need to make. One, adding a catalyst does nothing to the system in terms of the shift. It just makes everything move faster. But it's going to make the forward and the reverse move faster. Okay, so it's not going to really affect the system. Another thing that I wanted to point out is if you'll remember back to last lesson, we don't include solids or liquids in the equilibrium expression. So solids and liquids also cause no shift unless you're talking about adding solvent, like we talked about, that would dilute all your concentrations. So refer back to the notes for adding solvent. But if you have a pure solid or a pure liquid, if you're just adding a small amount of it, it does not affect the equilibrium as it would if it was aqueous or a gas. Also, when we increase and decrease the pressure of a system, we're doing that by volume changes. So when we increase the pressure, we're doing that by making the volume go down. And when we decrease the pressure, we're doing that by making the volume go up. If it talks about adding pressure some other way, like the pressure is increased by adding what they call an inert, I-N-E-R-T, inert gas, that doesn't cause any shift. Okay, what that's meaning is some gas that doesn't really react. So if you try to increase the pressure that way, I'm going to add that down here in the no shift, inert gas. If it says something about that, that does not cause a shift in the equilibrium. Okay, that should be going down toward this no shift. Sorry, that's not clear. No shift. All right, So there you have it. There's a good summary of what's going on. I want us to look at this sort of thing in the context of one reaction before we go. All right. So what we have here is an example reaction at the top, and then we're going to talk about a lot of stresses and how that would affect like each part of the system. All right. So let's start with the example that they gave, which was adding H2 or hydrogen. So if we take the system and we add some hydrogen, we would be adding a reactant. Remember, when you add something, you shift away from it. So we'd shift to the right. We're going to put a line across the H2, all right, because that's the thing that we added, so we know that it's going to go up. But if we have to shift to the right, that's going to make our I2 go down because it's a reactant, and our HI go up because it's a product, but this would not change K because adding or taking away things does not change our equilibrium constant. Only temperature can do that. All right, so let's go through another one. Adding I2. Okay, there's I2, a reactant. If you add something, you go away from it, so we'd be moving toward our products. If we move toward the products, that's going to make the H2 go down, and the HI would go up. The K then would remain the same. All right, what if we add the HI? Well, that's a product. So if you add a product, you shift toward the reactants to get rid of the excess. So that's going to make our H2 and our I2 go up. And of course, K would not be affected. All right, what if we remove something? If you remove something, you move toward it. So if we move the H2, we go toward it. That'd be going toward the reactants. Well, I2 is a reactant, so it would go up, but HI is a product, so it would go down, and then K would not be affected. If we remove I2, that's still a reactant, so we would go to the left. H2 is also a reactant, so it would go up. HI is a product, so it would go down to try to make more I2, and then K would remain the same. If you remove HI, you go toward the thing you're removing, and that's a product, so we'll go to the right. H2 is not a product, and we're going toward the products, so we go down to make more HI, and that again would not affect K. All right, if we increase the temperature, where's the heat? Where's the heat? The heat is a reactant. See right here, heat is on the reactant side. So if we increase the temperature, we're making more heat, so we move away from the heat. So we're going toward the products. These are products, H2 and I2, so they'd have to go down. HI is a product, so it would go up. And temperature is the only thing that can affect our K value. And we're going toward the products, and that would make K go up if you go toward the products, right? Products over reactants. All right, so if we decrease the temperature, where's the heat? The heat's on the reactant side, so we got to go make some more heat if we decrease the temperature. So we're going toward reactants. So our reactants are going up, product going down. If our reactants go up and our products go down, our K value's got to go down too. Temperature is the only thing that can change the K value. All right, what about pressure here? We said that if we increase the pressure, that's going to make the volume go down. We don't have enough space, so we got to go to the side where there are less gases. On the left-hand side, we have H2 and I2 gas. That's two gases. And on the right side, we have 2 HI. That's also two gases. So there's two gases on the left, two gases on the right. So if we increase the pressure, there's the same gases on both sides, so nothing happens. Also true if we decrease the pressure, because we have the same gases on the right and on the left. All right, so we've got a good summary there. Go back and review all the stresses, maybe copy down that last chart or something similar of your own. What are the stresses and how do they affect the equilibrium? All right, that is Le Chatelier's principle.